Well, hello again. This is the fourth and final part of my video series on induction motors, the AC induction motor with the squirrel cage rotor. And last time we showed these plots, but I didn't go in and actually show actual points. But let's just fix these in our head again. So this is the torque. Now, this is torque per phase, and this is power per phase. And this is the actual current. Now each phase is going to have this amount of current roughly starting out. So heavy current starting out, then it comes down. Here's your torques. Here I've drawn a line that if you have a constant torque load, okay, something like a hoist or something where the torque is constant, then basically this is the limit. You can't have a load any higher than this because it's got this. The startup torque is only this. So if it was above here, it wouldn't work. Now, if you had something like a fan torque, which is kind of like a quadratic, then of course it could come down and work somewhere here. But for constant torque type load, then basically this is the limit here for this. All right. And then we went in and expanded and looked at here. Let me just do this one more time. Okay, and as we can see, as the slip increases from 0.02 to 0.03 to 0.04, that what happens is obviously more current is drawn, and obviously the torque increases, and obviously the power increases. Okay, and what we saw is that if we have a constant torque type load, then there's no way we could operate it at a slip of 0.4, but we could possibly a slip of 3, and definitely at 0.2. Okay, now let's go. Let me close this out here, and let's go in and let's look at the actual values here. So let's run this again. Let me close this, and do this. Okay. Let's run it. Okay. And we'll put this over here to kind of look at it. Now remember, well, maybe you remember, maybe you don't, but let me remind you that in addition to the standard stuff that I plotted here, I also did the standard I-line calculation, okay? And that was the formula where you take the horsepower, multiply it by 746 watts, and then you divide it by the square root of 3 times the line-to-line voltage times efficiency times the power factor, okay? And so what I've done is I have those calculations down here, okay? And those are standard calculations for figuring out what the full load current would be. And so here, let's see how they match up with what we've done with our calculations here. So let's start out with a slip of 0.02, and let me go here and just expand this while we're watching this. Okay. And so here, if we get a slip of 0.02 here, then what we notice is that the transfer resistance, RT, which is 7.2, so this is the R rotor over S. Okay, this includes both the lossy part in the rotor and also the mechanical part, is 7.2. The actual current flowing in the stator, one of the stator wires or phases, would be 18.78 amps. The power, and here again, this is per phase, would be this. The torque is 15, and this is per phase again, so if you multiply this by 3, 45, that would be the torque produced by the motor. The power factor, 0.85, the motor efficiency, 0.86, and note though, I didn't actually go in and calculate specific losses like windage and bearing losses or anything like that. So, but anyway, if you go and do that standard calculation, then it calculates an amperage of about 26.8 amps as opposed to this. So that's quite a bit more than what we calculated there. Okay, so let's go to a slip of 0.3. Okay, if we go to slip of 0.3, then RT, which is, like I say, RR over S, is 4.8 ohms. The current's gone up to about 25. Okay, and the torque is 21, and here again 3 times that would be the motor torque. Power factor's gone up, which we saw. Motor efficiency about the same, and the calculation here is pretty much in line here. So for this particular motor, a slip of 0.3 is pretty close to your standard calculations for your line current. Okay. Now look what happens here when we go up to a slip of 0.04. Then this has gone down. The current now is about 32 amps. Torque has gone up to 27. Power factor a little bit higher. Motor efficiency about the same. But notice here the standard I-line calculation is less than what our model predicted. Okay, so just something to keep in mind, that the standard calculation that you see all over the internet, and a standard way of calculating your full load current, essentially is for this particular model works out closer for a slip of 0.3, so it's slip dependent. Okay. All right. So anyway, that's all I wanted to do with that. So let's go in and let me minimize this and these. Seems like I'm getting more files than I thought I had, and let's start doing some stuff in LTSpice. Okay. So let's start out by looking at this. So what we want to do is let's go in and see some stuff that's going on. So first thing I want to do is let's go ahead and let's simulate it. So let's go to here and run this, and I'm going to minimize this one, this, okay, and oops, I didn't want to do that. Okay, so let's try this again. Alright, so in here, let's run this. Alright, there we go. Alright, so the first thing I want to do is let's look at the voltage and the current. Okay, and here's my current. So this is the current's here, and so what I'm going to do is I'm going to make this bigger. Okay, and let's go over here. Go a little bit more. All right, so and if I go in and just expand it even more, notice what we see is we see that basically the voltage here, the line voltage, okay, this is the 127 volts RMS, and here's the actual current. That basically is lagging, the current's lagging the voltage, which means you have an inductive circuit, okay, which is what we expected, okay. And let's go in and let's actually go in and let's look at the phase shift here. So if we go here and let's go in and measure the phase shift here. All right, and go in and measure here. So what we want is we want the phase shift between here and there. So what we have here is we have a distance and time difference here of about 1.36 milliseconds. Okay, so to convert that to an angle, all we need to do is take that 1.358 milliseconds, divide it by the period of the waveform, which for 60 hertz is 16.67, and we multiply that by 360, and what we get is about a 30 degrees phase shift, which is, if I remember, about similar to what we had before. Okay, so we see the current lagging. Let's go in now and let's go in and let's measure this current. Let's look at this current here. So let's run it and let's see the current and see how that compares. Okay, now what I'm going to do is go in and use a feature built into LTSpice where if I hit the control key and I left mouse click, it'll give me the RMS. Okay, about 18.3 amps actually flowing here in the stator. Okay, so that's interesting. Now let's go in and let's look at the current here. Let's just decrease this, delete this trace. Okay, and let's go in and let's measure the current here. Alright, let's do the same thing. And this is about 16 amps, which I believe was pretty similar to what we were seeing with the other one. Now, notice that this value here corresponds to a slip of 0.02. Okay, and so these are currents that we'll see when we're at the operating range. Okay, so let's go back now and let's do the calculations where we had a slip of 1. Now, if we had a slip of 1, then essentially what's going to happen there is if we looked at the calculations, remember this times 1 minus s over s, okay, was the value. So let's go in and let's do that. Let's change this value. So instead of this, what we're going to have, and let me bring that back up just to refresh your memory here. And let's see, let's go back to here, slip. Okay, and so what we're talking about is slip here. Okay, so if we go in and we make this 1, okay, then obviously this is going to go to 0. This will go to 0 and we'll just have the RR, right? So let's go back. And so what I'm going to do is make this resistance 0 and just leave the RR. So let's do that. So let's close that out. And here I'm going to change this to 0 ohms. Okay, so let's rerun this and let's see what kind of currents we have now. Okay, so now we go in and calculate it, and let's do the same thing. Whoa, about 146 amps in the stator, and I think that's about what we saw before, about 150. So this corresponds to a slip of 1, which is at startup, okay, or locked rotor. So that's what we got for the stator currents. So 146, remember that. All right, let's go in and let's kill this here. 46. And let's go in and run the current through here. Let's do the same thing. And so about 144, so it's pretty close to the same thing, 146 versus 144. So really heavy current flowing through there, okay? Really heavy current flowing through there. Okay, so what we've done is we've shown that basically this is giving us pretty close to the same values that we got for the other. We could go in and look at power and some of the other stuff. We could multiply that out, but that's probably not the best thing to do on here. We could go in and create waveforms. Let's go in and instead, let's open this up. Instead, let's look at this one. And let's go in, and here again, we're at a slip of 0.02 or 0.02. All right, and let's just close this out here. All right, and so let's close this out, open this, and run it again. Okay. Oh well, if it wants to be on top, that's fine. Okay, so let's go in and let's look at some voltages here. So let's go in and let's look at first at this voltage here. Okay, and so that's the 127 or the about the 170, I believe it was, peak to peak. And now let's go in and compare that to the voltage here. Alright, and so if we look at this, this is the voltage line to line, and then this is the voltage from this particular line here. Okay, and so this corresponds to the 127 RMS. This corresponds to the 220 RMS. Okay, let's see, what else can we do here? Let's look at the different phases. Okay, so let's just kill these. All right, and so let's look at this phase and this phase and this phase. All right, so just expanding this, so these are the three phases coming in. Okay, these are the three phases applied to the circuit. All right, and you see the 127 phase voltages back and forth. They're all 120 degrees out of phase. Okay, if we go here and kill that, so let's expand this. Okay, and so what I want to do now is let's look at the currents, the line currents going in each one of these. And so let's run it. And so what I'm going to do is look at that current, and that current. Okay, and let's go down here. All right, and we can expand this. Okay, and here again I can just expand it some more. All right. So notice that although the line current is what we had, now let's go in and let's see, let's expand it out again. Let's go, say, from here to here. All right. And so let's actually calculate the current. So here again, I'm going to go to here, press the control key, press there's 18.8 amps. Okay, pretty close to what we saw before. So each one of these lines has an RMS value of that, but notice at any given time, because they're 120 out of phase, that, and a little bit of slippage here, probably need to let it run, simulate a little bit longer, but at any given time, you know, basically the actual current in any particular line is a little different, okay, because of the phase. Okay, so let's go back, and what do we want to do? Let's go in, let's change these back to 0. So this corresponds to a locked rotor. What we're doing now is doing simulations for like 0.02 slip. So if I go here and let's change this to 0. Okay, change this one to 0. And change this to 0. Okay, and let's see the change in the current. So let's go here, And let's put the current there, current there, current there, here again. We'll go from here. Right. Okay. And like I say, I could run it longer, but you'll get the idea. So let's go in and let's look at the actual currents that are flowing now. Okay, so I'm holding down the control key, left mouse clicking. Wow, 153 amps. Okay, so a big, big, big current here that's flowing through each one of these phases here. Okay, so locked rotor, or basically a rotor that's just starting up, you got a lot of current flowing. When you basically go in and you're at a slip of 0.2, 0.3, or 0.4, then essentially then it's going to be much slower. And for a slip of 0.2, we saw about 18 amps roughly for a starting out rotor, a locked rotor, around 150 or so. Okay, so that's pretty cool. Oh, the other thing that we talked about is if this is balanced, let's see what kind of current's flowing now. We probably want to go ahead and change the simulate so it runs a little bit longer this time so that things stabilize. So let's go back here to the edit simulation, and instead of stop time 1, let's do a stop time of 4 to give it plenty of time to actually simulate. Okay, and let's run it. And now, okay, let's go in and let's look at the current actually flowing through there. Well, as you can see, this is in femtoamps, which is that 10 to the minus 15th, whatever. It's really, really, really small. So there's practically no current flowing through here. Let's just verify there is current flowing through there, and through there, and through there. And as you can see, it hadn't really stabilized at 1 second. It was still kind of going on, but by letting it simulate a little bit longer, we got a little bit better simulation here. Okay, and so let's go in and let's hit the control key and press this, and yeah, so about 152 amps on each one. Okay, but so you know, and that's a property when you have three-phase imbalance, then you don't really need a neutral wire for this Y-type connection here. Okay, but if it's unbalanced or something happens, then you know you're going to get weird stuff. Okay, so let me just summarize these three videos. Essentially, what we did is we used this model, and so let's close this here, and let's open this back up. We use this model from the electric machinery book that I have by Fitzgerald and Kingsley and Cusco to actually see how a induction motor, a squirrel cage induction motor, works. And we use actual values that they provided, and actually they were very close to another source that I showed you for a 10 horsepower 220 volt 6-pole induction motor. Okay, and we actually produced torque speed curves. I still have those curves up there. If I go back and go back to the reset here, it produced these curves here. So we actually have our torque curve here, which goes according to this. This is the 0 for that. We did the power curve, which goes to here, 0 here. There's this 0 going here. So the torque's not 0 here, but there's the torque, here's the power, and then we talked about the current. So here we can see all the different curves, and the current is the actual current in each phase. Each phase has this current. Okay, and this torque here times 3 would be the torque produced by the motor, and this curve here times 3 would be the actual power, And we talked about the actual operation of the motor is down in here, maybe up as high as here. But this curve corresponds to a slip of 0.02 or 2%, 3%, and 4%. And what we discovered that for this particular motor here, that the max torque that we could get was somewhere around, 25 times 3, 75 roughly, if it was a constant load torque. If it was like a fan torque that kind of goes up like a quadratic, then we could actually run something like that. And anyway, this model explains the high current at startup, which means that if you're going to be working with this motor, you probably don't want to directly hook it offline. You probably want to use some type of soft start device, or maybe even a VFD, okay? And so those would be the subjects of some other videos, okay? So anyway, this concludes the video. I hope you enjoyed them. This is the end of part 4 and the end of my 4-part series on AC induction motors. And this one's shorter than the other, so that's great. I hope that you got out of this that there's a lot of great tools out there to do it, to do these kinds of simulation stuff. I am sold on Python. I've played around with it for a while, but with all the libraries like NumPy and SciPy and Matplotlib, my God, this is a wonderful tool, and it's free. So anyway, if you can make a contribution to that, definitely do it. It's really worth it. It's a great tool. Also, the LTSpice is a great tool to do a lot of simulations. So equations are fun and algebra is fun, but sometimes you have to kind of draw the line or draw the curve. And if you want to draw the line, draw the curve, then it's best to kind of go in and just do the minimum amount of algebra you have to, and use some great tools like Python and its libraries to actually go in and analyze stuff. Anyway, that's it. Have fun. Hopefully you learned something about induction motors. Bye-bye.